This is Bart Smith. I'm going to repeat my presentation from this Saberseminar 2019 in Boston on this recording so I can put it online. So the topic of my talk was what do baseball seams do to a ball in flight? My co-author is Andrew Smith. I should say that this will be a little longer than it was in my presentation because I'm going to try to do it at a reasonable pace. So just before I start, to acknowledge some folks that made this possible. This is Andrew Smith, my co-author. He's a graduate student in mechanical and aerospace engineering at Utah State. John helps him out. He's an undergrad. This is Nazmus Saqib, who built a lot of the infrastructure that we're using and did the preliminary study. So we wanted to acknowledge how important his work is to us. I wanted to thank Lloyd Smith and the Washington State Sports Science Lab for equipment and support, and Mike Fast, who sent us 6 dozen baseballs to test from the Atlanta Braves. We appreciate it. Okay, so here's a baseball. Anytime you have a bluff body and especially a flying sphere, the physics are very complicated and surprisingly complicated because it seems like a simple object, but it's not. In addition to that, baseballs are even more interesting because of the seam pattern and the raised seam. That's really a major point of this talk, is to show you what that seam does and some of the unique things it does compared to other sports balls. And what's funny to me is I don't think anybody ever had that in mind when they put the ball together this way. But we're lucky that they did, because it makes the way that they fly very interesting. So before I start, I want to explain some basic aerodynamics that are going to be required for you to understand a lot of what I'm going to show later on. The first thing I want to mention is that when you have airflow over a bluff body like a baseball, the flow on the front of that object is stable and the flow on the back of it is unstable. And when I say that, I want you to pay particular attention to how stable it is. Things are very stable on the front. They become less stable as you go around. They are not stable at all here, and they become unstable as we go around the back. That's what this gradient down here is meant to indicate. And so when I say stable, what I'm talking about is whether or not if the flow is laminar, it's going to want to stay laminar. It will if it's stable. And if the flow is separated or attached, the boundary layer is attached, if it will tend to want to stay that way. And I haven't explained what boundary layer means. I'll come to that in just a minute. But basically, stable means things are going to stay the way they are, and unstable means things are going to change. And there's a couple different things that can change, and they interact with each other, which is the complicated physics I was referring to before. So first, how we launch the ball. We use this cannon from Washington State University, and this is really a critical piece to our work because this allows us to do several things. We can launch the ball without damaging it like a pitching machine would do, and we can repeat its orientation really accurately. So that's been a huge plus for this study. In fact, the study wouldn't be possible without it. This thing's capable of ridiculous launch speeds. We're shooting everything at about 90 miles an hour for this study. And here is John and Andrew in the lab sneaking in a Texas Rangers game and about to launch a ball. This is an older cannon that we don't use anymore, but this big black box here contains our measurement system. Andrew asked me to point out if there's any major league teams, we are happy to put your signage up here if you provide it. This one was provided by my son Sam, whose wall I stole it off of without his knowledge. So this is what's inside the box. Unfortunately, a lot of the important things are hard to see here, but there's a laser here and a laser below. So we illuminate the ball from above and below as it goes by. There's a camera here that takes a picture of the ball as it goes by. And we have a smoke machine down here that provides the particles that we're going to use to determine the air velocity. When we fire a ball into the tent, this will play over and over again, you can see that briefly the ball blocks those 2 red beams, and if it hits both of those, then the system knows that it's in position to take a picture. And the green lasers both fire, actually twice, to illuminate the ball. And those two, so we end up with 2 pictures of the ball, and here are an example of 2 pictures, along with the smoke particles that are in the air, or fog particles really. And we use these to determine the velocity of the air at every location. Now, this recording is really meant for laypersons, not fluid dynamicists, so I'm not going to go into explaining how we use these pictures to determine the velocity. I'll just say some magic happens. And when we do that magic, we end up with a picture maybe like this. This is one of our old data pictures that Nasmus took. This is a high school baseball. It's in a two-seam configuration, and we're looking at it from above. So it's rotating at about I think it was 1600 RPM, and it's rotating in a fastball configuration. So the top is moving to the right, the ball is moving to the left. So there's several things I want to explain here about aerodynamics that are important. First of all, I mentioned the concept of a boundary layer earlier. A boundary layer is the region where the velocity changes really rapidly. And you can see that the velocity, I should mention the color here, it means velocity. And the red is a very high velocity. And so on the front of the ball, we see red, and then it very quickly turns to blue. That is the boundary layer. That's the region where the velocity changes from what we see out in space to what we have near the object. And that region, that boundary layer stays attached to the ball as we move around the ball. But when we get into this unstable region, at some point it will separate. And that's really what I'm focused on in this study, is where that location is. I'll talk about why in just a second, but we're going to be looking for where does the boundary layer come off the ball, because when that happens, we form a wake, and we're very interested in the wakes in this study. So what do we care about with respect to the wake? Two things in particular. I want to know how wide it is, or how wide the ball is where the boundary layer separates. That dictates how wide the wake is, and how wide the wake is a qualitative indicator of the amount of drag we have. If I have a bigger wake, I have a bigger drag than if I have a smaller one. If the wake is tilted, that's an indicator that there is a transverse force on the ball, and you can draw a line from the back of the wake to the ball, and the force is in that direction essentially. So there's a component pushing this ball to the side. I'll talk a little later about what I think is going to happen to this ball. Cutting to the chase, it's going to continue to go straight in spite of that, because that wake is not steady. It's going to flop back and forth. In most of these slides, though, I'm not going to present colors that indicate velocity like that last plot. I like to use what we call vorticity, which is a pretty flowery fluid dynamics term. It's basically how much the air is spinning. Blue means it's spinning clockwise, and red is counterclockwise. But that's really not important at all to what I'm going to be talking about. But vorticity does give us a very clear indication of where the boundary layer separates. So that's why I like to use it. The separation points where I'm pointing here on the top of the ball on the blue, and on the bottom of the ball here on the red. Sometimes that point is more clear than others, but it's easy for me to see where that's formed. And all I care about here is how big the wake is and how big it was when the separation occurred. So don't worry about blue versus red. Doesn't really matter. I also want to mention, if you see any color on the front of the ball, that's probably just measurement error. Nothing of much interest happens on the front of the ball anyway, so ignore that. Okay, so I'm starting with a smooth ball. We printed this out of plastic, and it's about the size and weight of a real baseball, and it's polished up to be very smooth. And if I do that, even at 90 miles an hour, this flow, the boundary layer separates, and it separates while it's laminar, meaning that laminar means it's smooth and not fluctuating in time. And laminar boundary layer separations on bluff bodies like balls generate very large wakes and a lot of drag. So this is counterintuitive to a lot of people, that a smooth object is going to have a very high drag because the boundary layers separate. It's news to a lot of people that the drag on an object like this is mostly because of the wake and has very little to do with skin friction. That's a common misconception that I run into, is people think about the skin friction, and it really does not matter very much. It's a very small percentage of the total drag. So this big wake is generating a lot of drag. This, by the way, is why they dimple golf balls, is to prevent this situation from happening. We wanted to do this particular case, though, so that we would know what laminar boundary layer separation looks like, because we do occasionally see it on baseballs. And here's an example, a very zoomed in picture of a baseball. It's in a two-seam configuration, and the seam is curving back towards the front of the ball, so there is no seam on the front of the ball in this case. It's very smooth. And so we have this very distinctive laminar boundary layer separation and a very big wake. if I change the orientation of the ball so there is a seam on the front of the ball, and I should mention this ball is moving to the left. It's not necessarily obvious in these pictures. All these balls are moving to the left. So I have a seam in front. It disturbs the flow. The flow becomes turbulent up here, and it remains attached until about where I've indicated with an arrow here. So this is going to give me a much smaller drag. Now, if I have a baseball that's been abused, this one has been through a pitching machine many times. I get the even with no seam on the front, I get a turbulent boundary layer separation. So this is what made us realize that our early work was all needed to be repeated, because we were using baseballs that look like this one, and we lose this richness of having the ability to have laminar or turbulent flow depending on whether or not there's a seam on the front. So concluding this slide, there's the three things that I've told you. If we don't have a seam on the front, we have a laminar separation in a big wake. If we have a seam on the front, we have a turbulent separation in a small wake. If the ball is scuffed, the flow is always turbulent. So here is a 2019 Major League Baseball, and we're looking at it a much more zoomed out view now. And what we see here is that the flow, the seams on the front of the ball have caused the flow to become turbulent here. We have a separation. That separation point is on the back of the ball. It's on the back of the ball over here too. We have turbulent flow on the bottom. So I said that the seam on the front will cause the flow to be turbulent. We find that sometimes it's turbulent even without a seam, as in this case. If I rotate that ball just a little bit, now you see that that boundary layer separation point is on that seam. The bottom hasn't changed, but the top has. And you can see as I rotate that seam further that the shape of the wake is changing, and it's actually deflecting downward a little bit, and even more if I rotate that more. If I continue to rotate it, at some point, the boundary layer separation point comes off the seam. But the major point here is you can see how that seam controls the boundary layer separation point over a range of angles. I can't prove it right now because I don't have this parameter dialed in, but it's my contention that the larger that seam is, the bigger the range of angles is that will stay attached. And this, as you might have heard, is the smallest seam ever probably on a baseball for the 2019 baseball. So if I rotate that around in more of a four-seam configuration, I can see a lot of the same thing. I have turbulent flow over the top and bottom, which makes sense because I have these seams in a not super stable region on the front. If this seam were here, the flow here could still be laminar, but it will not stay laminar if I put a seam this far into the less stable region. As I rotate the ball a little bit, you can see that this boundary layer is becoming attracted to that seam, and if I go further, it's right on that seam. And then if I go too far, it's no longer attached to it, but now it's picked up on the top one, and that will continue as I roll further along, and now it's detached from the top and attached to the bottom. So if I run through that, you see that that's causing the wake to oscillate quite a bit up and down. And I think that this happens when the ball flies all the time. The wake is both because of the seams and because of some natural instabilities, it's flapping around. If it flaps around, the ball is way too heavy to respond to that, so it's not going to have any effect on the flight of the ball in terms of pushing it left or right or up or down. But the drag that the ball experiences is some kind of average of all these states. So I wanted to compare a very low seam ball. Here's a 2019 Major League Baseball to a very high seam ball. This is a defunct NCAA high seam ball that was used a few years ago. They've gone to a lower seam ball now, but notice the huge difference between these two flows and how much larger the wake is for the high seam ball. And in this case, the flow is actually separating from the front of the ball, making a huge wake off of this very big seam. One other thing I wanted to point out, here's that same high seam ball, and here's an orientation where it has a seam on the top and the bottom, and again, it's making the wake probably about as big as it could be. And if I rotate that just slightly, the wake is much smaller because it's now detaching from the back of the ball on both sides. So what I take from this is that seams can change the drag of the ball, and that effect happens over a very narrow range of angles. So I think most of the time, the Major League ball and the high seam ball are going to be the same, but in these certain orientations, they're going to be very, very different. And those orientations don't last very long, but they can significantly change the aerodynamics of the ball in the average. But the main reason I'm interested in this today is I'm very interested in this idea of that's been called a Laminar Express pitch. It's basically a two-seam fastball that has some gyro spin to it. The video here is from a study that we did with driveline baseball that came out to Utah State. They threw 400 pitches through our PIV machine until they got 3 that hit the right spot. It's a very narrow region that they needed to hit with the baseball. And here's one example where they did it. So you can see that ball does have some gyro spin to it. That or in other words, it looks a little bit sideways, and there is a smooth side on the left. That's what led Trevor Bauer to claim that side of the ball has laminar flow. I've sketched it over here, and I think Trevor's incorrect about that, because in that configuration there is a seam just upstream of the middle of the ball, and that's definitely going to make that side turbulent. And from what you've seen so far, hopefully you remember that turbulent flow is going to separate further back on the ball than laminar flow. The interesting thing, and I think what people have been missing about this pitch, is that in that same time there will be a seam on the back of the ball on this side, and that's going to cause that flow to separate earlier than it would have without a seam there if the flow were turbulent. And so I think that can create a wake that is sideways and generates a side force on the ball. There is Magnus effect going on here. That's in the other plane. So this ball is spinning along this axis, and so the wake is going to be tilted downward also out of the page. But then this, if I'm right about this, then this gets added. This effect gets added to that, and it's going to cause the ball to move sideways a little more than it would have. So this is still a little bit controversial whether this is happening or not. Analysts that look at pitch data constantly tell me that they've never seen anything in the data that indicates that something other than Magnus effect is going on. I am a little skeptical about some of that data, and that I'm worried that the data, by the time we get the data, there's been some model applied to it that prevents us from seeing that. So at the end of the day, here's my current attitude towards the Laminar Express. I want to believe it exists, and I think I've seen that. I've repeated one of these pictures from earlier to say why I think it can exist. Here's an example of a tilted wake, because there's a seam on this side, turbulent flow separation on that side, and if this ball were spinning along this axis, this would be steady, and or it would at least be there about 3/4 of the time as those seams rotate around. I think that's enough to create a side force. So I've seen anecdotal evidence of pitches that behaved very strangely, and I think that this could explain it. And the question is, why do we see it so rarely? And I think that right now that's still an open question. So here's some conclusions. We have a stable front of the ball and cause turbulence, but if the seam's on the front, it can cause the flow to become turbulent but not separate. The high seam ball seemed to have the ability the seam had the ability to cause separation on the front of the ball. The MLB baseball seam near the rear of the ball can control boundary layer separation and therefore the wake, and that might be useful for a Laminar Express, but there's nothing laminar about the Laminar Express. So thanks for listening. I have a website that you can check out, baseballaero.com, where we put a lot of this information, and I hope you have a look. Thanks for listening.